Hello, guys. Welcome to the new session of Group Theory in Vibrational Spectroscopy Part 1. This is entirely a new topic that we're leading in, and I hope you would enjoy this journey. I'm your instructor, Saurabh, and let's proceed. We are talking about the use of group theory, applications of group theory in IR spectra, and we know that IR spectral data are blueprint of molecular vibrations. So, group theory provides an inner vision, inner sight for analysis of such vibrations, and also gives a theory. This theory provides a concrete theoretical base to the idea. So, let's proceed to learn more. We know that molecules vibrate with characteristic frequencies, and their frequencies are noted, and thereby we can decide the kind of various groups that are associated in that particular compound. These frequencies fall in the region of infrared spectrum of electromagnetic radiations, and these molecular vibrations are nothing but the relative motions of atoms with respect to each other. So the molecular vibrations actually define the energy states of the molecules, which are of course quantized, and group theory can help us to identify which molecular vibrates can really exist, as we are talking about the displacement of the atoms in a molecule and the symmetry changes that are taking place. But the question is how this can be done, and the answer is very simple. First, identify the point group of the molecule, generate a reducible representation by considering every atom of the molecule in a 3D Cartesian coordinate system. Refer to the character table of the molecule that is we are talking about, and decompose the irreducible representation as the sum of irreducible representation using standard direction formulas. So what we have to do is first we have to generate the reducible representations taking the basis for the molecule on a 3 Cartesian coordinate system. Once we are done with that, subtract rotational and translational representations from that and obtain the vibrational symmetries correspondingly. So it's that simple. Again, taking help from character table, you can predict the IR and Raman activity of the molecular vibrations. How? So start with a simple molecule. Again, we have been talking about C2V molecule, water molecule as a simplest case that we can start with studying in. And there are 4 symmetry elements: identity, C2, sigma V, and sigma V dash, etc. So there are 4 symmetry elements, and just look at the character table for same. You have C2, sigma XZ, and sigma Y dash. This is what sigma V dash we talk about. And there are 4 irreducible representations: A1, A2, B1, B2, with the characters we can see from the table itself. Now what we have to do is we have to think of every atom of the molecule that is there in the system. For instance, this is the oxygen. Now this is Z2 axis for oxygen, X2, and this is Y2 for oxygen atom. For this first, this is hydrogen atom. So this is Z1 for the first coordinate. X1 is here and Y1 is here. Similarly, you have Z3 is the principal axis. You have X3 and you have the Y3. So each atom has been decomposed into 3-dimensional coordinate system. This is the C2 axis from which we are making a rotation. So we are making rotation along the z-axis. And if you are using this plane, you can understand that this plane has to be a xz plane. And if you're talking about this plane, which includes, this was y-axis, so this has to be a yz plane. So you have yz and xz planes, and see what happens now. As every atom has been assigned in a 3 Cartesian coordinate system, we know that for identity, we can decompose this matrix into we can construct a matrix of order 9 by 9. How? Look at this. For identity, we know that each matrix has a representation system of 1, 0, 0, 0, 1, 0, and 0, 0, 1. So in the case of x1, y1, z1, and x1 dash, y1, and z1 dash, the coordinates remain same. So you get the identity matrix written over here at this point. Similarly, for second atom remains at the place of second atom, the dimensions would be same for identity, and the third atom remains for the third atom. So x3, y3, z3, and x3 dash, y3, and z3 dash are same. So what we get is this. And if we wish to identify or notice the character of this entire matrix, we know that character is defined as the diagonal sum of the elements. Well, as far as the rest of the elements are concerned, they are zeros, and you just see this matrix done. Now the next job is to get the character of this entire matrix. What we have to do is simply the diagonal sum. So you add them all diagonally, there are 9 ones, and total character would be equal to 9. So that's very simple for identity. Now we have to see how does under a C2 symmetry the things go on. For a C2 matrix for water molecule, it has to be written as this. When we rotate along the z-axis, the coordinates of z do not alter, but the coordinates of x and y are transformed. So they are -1, and 1 for one simple molecule. But then we are talking about a case where each atom in the molecule has to be seen in the 3 Cartesian coordinate system. So what we see here, that x goes to -x, y goes to -y, but z is of course constant. Now what we do for C2, now C2 we have 3 systems here, the old coordinates and the new coordinates. Here, in case of C2, what we see is only oxygen atoms remain unshifted. That means when you are rotating a molecule through a C2 axis, first atom goes to third atom. So what you will find here is that the second atom has not been changed. So C2 character, C2 matrix has the same orientation. However, the first atom goes in the place of third atom, and the third goes in the place of first atom. So you find here that this has been shifted this way, and similarly the first is transformed to third position, and rest of the elements are of course zeros. Now as far as the character is concerned, what we have to do is simply go for the diagonal sum, and you will find that the diagonal sum comes out to be the -1. There are 2 -1, this is +1, so it goes to -1. Let us see how another symmetry elements get transformed. The next case would be case of a YZ plane, as we have described. If we are choosing a YZ plane, the coordinates of y and z are not going to change, as y and z are contained in the plane. What would change is of course x. So because we are choosing a plane of kind YZ in a mirror, the coordinates of x would change. So that's how only x goes to -x, and the rest of things are as such. And you also see that when you're choosing YZ plane, the atom 1 is reflected by atom 3. Similarly, the third atom remains reflected by atom 1, and the atom 2, that is oxygen, is not being shifted. So what we start with, we have a matrix of 9 by 9 order matrix, and then what has not been changed is x2, y2, z2 and x2 dash y2, z2. So the second atom is lying in its own place. The only difference is that the third is being replaced by 1, and the first atom is being replaced by the third atom. Rest elements are zeros, so there is no point in considering them. They are zeros, and then you should go for computing the character. Character would be the diagonal sum. So let's do it again, and you'll find that this time the character is actually +1. There are -1, 1, but it becomes 0 plus 1. So for character of YZ happens to be +1. Now the last element, that is sigma xz. The sigma xz is typically different. Now it is different in the sense that it does not exchange its area. Instead, only half part from the front side goes to back side, from rear side. So, and because it is an xz plane, the coordinates of only y are going to get altered. So you just see x is +1 only y is changing. So I am writing the -1. But z is again +1 because the coordinates of y, x and z are not changing, only y would change. And further, each atom would remain in its position. So the distinctive feature of this is like this. So the atom 1 is in its original place. So this matrix determines this order here. Similarly, second in the place of second system, and the third in the place of third system. So there's no exchange of atoms only. What has been observed is only y is getting inverted. So these 3 matrices or these 3 systems are in the way they are shown, and the rest of the elements are of course zeros. So if you go for diagonal addition of this to obtain the character, what you'll find is sigma xz. So what we have seen is we have got the character table and we have got some characters. For identity, we have got 9. For C2, it is -1. For sigma xz, it is +1. And sigma yz, it is +3. Now, 9 minus 1, 1 and 3 are not the characters of any of the irreducible representations that have been mentioned here. So obviously, there should be a reducible representation taken as a basis for every atom to decompose in a 3D coordinate system. So the first task, our most important task, is to obtain the reducible representation. And once we are done with it, the next job would be to obtain the irreducible representation for the reducible representation. So with the standard reduction formula, it is going to be possible to show the reducible representation as the sum of irreducible representations. As you know, we have been using this formula in many times. So AI is number of times that ith irreducible representation has appeared. 1 upon h is the order of that particular point group, that is total number of symmetry elements. Chi I r and chi j are respectively form one of the reducible and one of the irreducible component. And this way you can compute the total representations or a reducible representation as the sum of the irreducible representation. This is a standard reduction formula that we are generally using. So if you want to calculate it now, you just start doing it. Here it was 9, so 9 into 1, so here 9 into 1 into 1, that is 9. Then here is -1, so -1 into 1 into 1, that is -1. And similarly, if here was +1, so here 1 into 1 into 1, that becomes as a +1. And the next case, 3 was here, so 3 into 1 into 1, that is 3. So 9 minus 1 plus 1 plus 3, and that's all, is equal to 12 by 4, that is equal to 3. And similarly, you can compute for other elements as well. Just look at this. How can you do it? For A2 representation, it is 9 minus 1 minus 3, it happens to be 1. For A3, it is, or for the A3, or rather B1 in our system, is 9 minus 1 plus 1 minus 3, that's 2. And 9 minus 1, that's +1. Again minus 1, then plus 3 is 3. So that is how we can see that each representation has been decomposed and a reducible representation can be shown as the sum of irreducible components. I hope that this is sufficient for you at this moment. We will proceed for other dimensions in the next video. Thanks for watching and see you in the next video.